doing this to bigger and bigger numbers, these numbers start to lock in. So like the 7 will lock in and never change, then the 1 will never change, and then the 8 will never change, and so on and so forth. Do you see that's how you get more decimals of E? Is just taking bigger and bigger numbers for n. Make sense? All right.
Is there one for pi too?
I'm glad you asked that question because I was just about to show you something. Just about to show you something. All right. So the question was, is there one for pi? So let's say that you're at some shady bar or something. Someone pulls you out into the alley, puts you up against the wall, and they want to know, the precise definition of pi, right? They demand the precise definition of pi. You see it happening, right? I mean, these things happen more frequently than you would think. So what is the precise definition of pi? Because I just gave us the precise definition of E. E is exactly defined to be a limit. And this is the first time this has ever happened. You have never defined a number ever in your life as a limit before. But we are defining E to be this number. All right? But if someone wanted to know what pi is, fortunately for us, it is not a limit. It is this simple. It is, if you take a circle and the diameter goes all the way across, right? Diameter goes all the way. Radius is halfway. Circumference is all the way around. Pi is exactly the circumference divided by the diameter. That is the definition of pi. It is a circle's circumference divided by its diameter. And that's simply taken from the formula, circumference is 2 pi r, right? But twice the radius is diameter. So circumference is diameter times pi. And if you divide both sides by diameter, then you get pi. So that is a simple way of expressing pi. Unfortunately, I can't give you decimals from this. Like, see with this, all I have to do is plug in values of n, and I can start kicking out decimals for E. There are formulas to get pi, similar formulas to get pi, but this is the cleanest definition of pi. While we're at this, there's a couple of other numbers that you may have dealt with in your life that are important. How about 1 and 0? I know these don't seem as important as these, right? But in mathematics, these two numbers are very important. We've used these before. Haven't we multiplied things by 1 and we just it was anything over itself? Like we came in with something and we put a 1 in there just to make things work? Or there was even some things I showed you with some proofs where we added and subtracted something, a hidden 0. But more basic, this is what's known in our mathematical system as the multiplicative identity. It's the number that when you multiply any number times this number, it doesn't change the number, right? 4 times 1 is 4. X times 1 is X. So we have a number within our number system that when you multiply times anything, it doesn't change anything. And this one is called the additive identity. Because when you add 0 to anything, nothing happens, right? 4 plus 0 is still 4. These two numbers are really, really important. These two numbers you've seen in your life as being important. You've been told, you know this is important. You've been told this is important, right? All right, so the reason why I'm showing you those is because I want to show you what has been argued to be, I'm not saying it is, what has been, oh, there's one more number, sorry. I, you've seen that before. It's this imaginary thing, and it's defined to be the square root of -1. Y'all seen that before? Okay, and y'all talked about that in college algebra a little bit. Well, we don't really go deep into it, and I'm not going to go into it today, all right? But you've been told that this imaginary unit is square root of -1. So I'm now going to show you what is argued to be, not by me, but by a lot of people, to be the most beautiful equation in math. All right, here it is. E raised to the I pi plus 1 equals 0. That's argued to be the most beautiful equation in mathematics. Why do you think they call that the most beautiful equation in math? It contains all the real nice numbers. It has e, I, pi, 1, and 0 all in the same place. And the equation is actually true. That is a true statement.
Is there a name for it?
I don't think there's a name for this. It's a result of Euler's formula for complex numbers. Yeah, I don't think there's a name. What this is really saying to you is this, though. Isn't this equation really implying this? That that's -1? Yeah, isn't that what that's really saying? Which is true. This is also a true equation, but if you write it this way, then it gets all the nice numbers in there. It gets the 0 in there, the 1 in there. So there it is. I don't know. I think it's nice. I don't think it's the most beautiful equation math, but pardon? Oh, I can try and make you believe something. If I can make you believe something, but you'll have to take it on kind of a little bit on faith. Yeah, we're going way off on tangent right now. Okay, this is the real number line, right? The real numbers? Okay. The complex numbers. The complex numbers are complicated, right? Because they include roots of negatives. In order to visualize a real number, like if I wanted to take the number 4, in order to visualize that, you need a number line, and you need 0, and then you can put 4 there, and you say, there's 4, right? But if I give you a complex number, like the number 2 plus 4i, that's what complex numbers look like. You actually need 2 dimensions to visualize them. You need 2 dimensions. So you have, this 2 plus 4i means you would go out 2, and you would go up 1, 2, 3, 4. Here's 4. And we could visualize this complex number in 2-dimensional space. So let's try and wrap our heads around that. A real number requires 1 dimension. A complex number requires 2. Understand? Now, another way I could represent this number is by giving you the radius, in other words, how far to go out to get to it, and the angle theta. Right? This goes back to pre-cal. If you have a point in 2-dimensional space, you can give me the x and the y coordinate, or you can give me the angle and how far to walk out. Well, there is a very important formula in complex numbers. Or not formula, yeah, I guess you could say it's a formula. It says this. Z equals r e to the I theta. All right, so think about this number right here. This point right here. One way to get to it would be to walk out 2 and go up 4. With me? Another way to get to it would be to rotate through this angle and walk out this radius. That would be the formula for that point. R would be this length, and theta would be that angle. With me? Okay, let's go back to this right here. According to that, what's my radius? On this, forget that. What's the radius here? What's the number in front of the E? 1, right? And then what's the angle? Pi, right? So this says, starting here, forget this. Starting here, you always start oriented this way. I want you to walk out 1 and rotate by what? Pi. And where are you going to land? Right there. What is that number? -1. Yeah, I know, it's pretty, this is awesome. This stuff is awesome. All right? That's pretty, it's crazy. Watch this. You want to stump, you want to stump somebody? Like you have a friend who's like a good at math? You can stump a lot of people with this one. I to the I. What's I raised to the I? That's saying what's root 1, the square root of -1 raised to the square root of -1. You will stump most people. Even if they're good at math, you'll stump most of them with that. Okay, so let me explain what the answer is. All right? So check this out. You have to first understand where I is on this, okay? So where is I? If I write I can really write that as 0 plus I. To just bear with me here. Remember I had 2 plus 4i a second ago and we went out 2 and up 4? Put a point. If I write just I, then that means I'm not going to move left or right. I'm just going to go up by 1. Does that make sense? So that means I'm here, right? That's I. We call this the imaginary axis, by the way, in complex numbers. This is the real axis and the imaginary axis. So this is the number I, right? Can you tell me what this number is written in this form right here? What is it? What would this number be written in that form right there? What's the radius? 1. What's the angle that gets you there? So you put I and then you put 90, so you put pi over 2, right? Isn't that I? That's what I is. It's weird, but I is equal to e to the I times pi over 2. With me? Now, I'm going to take this right here. I'm going to take this right here, I to the I, and I'm going to rewrite it as e to the I times pi over 2. That's what I is, right? Raised to the I. Agreed? Yes. Now, when you take something and raise it to a power, what do you do to these powers? Multiply them. What's I times I? I squared. What's I squared? -1. Right? If I is root -1, then I squared is -1. So this I and this I multiply, so you get e to the -1 times pi over 2. So e to the negative pi over, e raised to negative pi over 2 is I to the I. That's pretty cool, huh? Yeah. So look, if you're interested in this stuff, you have to get through all the calculus sequence, and then you take differential equations, and you take linear algebra, and no, and then you take a class called complex variables. Complex variables, and you've got me way off today. Sorry. We should be doing L'Hopital in here right now, but this to me is interesting. So look, complex. I just want to tell you why we don't study it here. Okay, it's not that we don't want to. Trust me, I want to talk about this. But here's why. If you take a real number, like let's take a function, f of x is x squared. Y'all are not allowed to talk about complex numbers ever again in this class, okay? You found my weakness. Okay. All right, f of x is x squared. Then we have a function, right? You take an x and it spits out x squared. So if we take 2, it spits out 4, right? Take 3, it spits out 9. All right, we like to visualize things, don't we? We're visual people. So what we do is we draw it. And this axis is the input, and this is the output, isn't it? So this is a real number, and this is a real number. This is an in, and this is an out. So if I plug in 2, I go 2 here, then I go 4 here, and that's the point, right? If I plug in 3, I get 9. If I put them all together, I get a parabola, right? That's the visualization of that function x squared. Yes? One of the axes was the input, one of them was the output. Good? Okay. When we are talking about complex numbers, if I give you a complex number, like 2 plus 4i, if you were to draw that number for me, it would require you put it right here, right? Now, what if I wanted to do a function that took this input, we call it z, we don't call it x, okay? And we square it. What's the problem with that? If I want to visualize this function, what's wrong? Okay, what am I going to need to visualize the input? This, right? What am I going to need to visualize the output? Well, the output's going to be another complex number, right? So I'm going to need 2 dimensions to represent the input and 2 dimensions to represent the output, which means the graph of this function requires 4 dimensions. Understand? 2 for the in, 2 for the out. Here, we only need 1 dimension for the input, 1 dimension for the output, and so we can visualize it 2-dimensionally. Yes? But with complex numbers, if you need 2 for in and 2 for out, 4 dimensions to visualize it, can't do it. Can't visualize it. Unless somebody can visualize 4-dimensional space. Yeah, what's the 4th dimension? So we live in 3-dimensional physical space, right? Usually we talk about time as being the fourth dimension. So do you see how things are going to start to get really complicated when you can't visualize these functions anymore? Right? That's why we wait till after calculus, after linear algebra, after differential equations. You've gotten yourself to a maturity level, mental, mathematical maturity level, where you're ready to start dealing with things that you can't see anymore. All right? So it's tougher. Do you understand that? And then what you realize later is that you don't, this function right here is what we call a function that takes a real number and spits out a real number. Okay? Real number in, real number out. For a complex function like that, it would be complex numbers into complex numbers. We use a script Z. But that really requires two-dimensional space into two-dimensional space. So to visualize that, you need 4 dimensions. Right? Here you needed 2 because these were each 1. But in general, in mathematics, you can have any function from any dimensional space into any other dimensional space. You could have something that takes in 10 inputs and spits out 4 outputs. You could have 100 inputs and 1,000 outputs. Think about the weather prediction, right? Computers. They take in all these variables, right? And they spit out all these results. These are very complicated functions that live in spaces that we can't see them. Yeah? Okay. Yeah, sorry. We need to go back, right? Thank you. Thank you. So what else do you need to see? How about, what was another one of those? What's one of the examples I gave you that we didn't do? Didn't we have like a cosine x to something? Limit. What was the limit approaching? 0. X approaches 0 from the right of cosine x to 1 over x squared?
Yeah.
Okay. All right. I to the I. Yeah, this is kind of boring now. This is going to be 1 to the 0, which is an indeterminate form, right? Wait, hold on. 1 to the infinity. I'm like, wait a minute, that's not indeterminate. All right. So we're going to bring in the natural log on both sides, and we're going to drop the exponent. And I'm going to do it all in one step. So I'm going to do natural log both sides. Like I'm going to call this y. So natural log y equals limit x approaches 0 from the right. I'm bringing down the 1 over x squared in front. And then I have natural log of cosine of x. Did I do too much there in one step, or is that all right? It's okay? Let's double check to make sure we do have an indeterminate form still. You will always have an indeterminate form. I mean, you don't have to check this, but I'm doing it just to try and convince you that this is good, all right? This is approaching what? Infinity? Okay. And then this right here, cosine of 0 is 1, natural log of 1 is 0. So infinity times 0, that's bad still, right? So now I'm going to take 1 and drop 1. And I think the easiest one to drop would be the 1 over x squared. Because what would happen if you dropped 1 over x squared? What would it actually turn out to be on the bottom? Be careful. Just x squared. It's just x squared because you're actually doing 1 over x squared, so when it drops it's really x squared. And now if you double check again, x goes to 0, you get cosine 0 is 1, natural log of 1 is 0, so you get 0 of 0. So you can do L'Hopital. What is the derivative of the top there? 1 over cosine x times negative sine x. And then derivative of the bottom, 2x.
Top is negative tangent.
Okay, you want me to write that? I'll go ahead and write that. We have natural log y equals limit x goes to 0 from the right of negative tangent x, I'm happy with doing that, over 2x. Let x go to 0 again. What's tangent of 0? What's tangent of 0? 0. There's your tangent function. Tangent of 0 is 0. On the bottom, we're getting 0. 0 over 0 still. L'Hopital again. Okay? That was one of the great things about L'Hopital, is that you could repeat it so long as you still have the form. What is the derivative of the top? Negative secant squared x. Derivative of tangent is secant squared, but we had a negative up there. And what's derivative of 2x? 2. Try it again. What is secant of 0? We'll wait on the squared. What's secant of 0? 1. Right? Because remember, secant is 1 over cosine. So if I plug in 0 here, cosine of 0 is 1, 1 over 1 is 1. So secant of 0 is 1, squared, 1, negative. And then 2 on the bottom, right? So we get negative 1/2. We're not done. We have natural log y equals negative 1/2. Now e on both sides. And you should get y is equal to e to the negative 1/2. Your answer is e to the negative 1/2. That's kind of crazy that this limit spits out, like the base wants to be 1, right? The base is like, I want to be 1. And then the exponent's like, I want to make you big. And they settle, right? They compromise. They compromise, but they compromise on such a weird number. They're like, okay, we'll meet somewhere in the middle. We'll meet at e to the negative 1/2. Okay, that's what happens. All right. Where's my sign-in sheet? Are we behind? I feel like we're behind. Today is the 26th. Oh no, well, we're not behind at all. We're ahead.
Let's keep talking about complex.
Yeah, no, we're supposed to start L'Hopital's rule today. Oh, right? It's because I went so quickly through the log stuff. All right, let's pass this around. Y'all haven't signed in forever, but just sign in on the most recent, the last column here, just sign in there, even though the date says March 7th. All right, homework for this section. Where's my book? The homework for this section on 3.8. Should be. We still have 10 minutes. How about I just throw a random problem up here for you. See if you can do it. You'll get extra bonus points in your brain. For all right, how about limit as x approaches 0 from the right of sine x times natural log x. And then another one, limit as x approaches 0 from the right of tangent 2x raised to the x. So we only have about, what, 7 minutes left? See if you can't get at least that first one done. And the other one's up there, just, if you finish the first one, give you something to work on. Make sure you get your homework going for this section, all right? We'll come back, I'll answer any questions we have, and if y'all are ready to move on, we'll move on to the next section, next class. This isn't a quiz. Y'all can talk to each other, and it's just practice. Does that sign-in sheet get around to everyone? Yep, okay. No, over here? There, yeah, we're fine. We're just fine over here. Is that first one going? Is it working?
What? Oh, you did that.
You do get 0 times infinity up here, or 0 times negative infinity. So you have to drop one of them. I chose to drop the sign. I think it might be easier that way. And I rewrote 1 over sine as cosecant. Right? Isn't that the same thing?
Yeah.
And now you can do derivative of top and bottom. What is a derivative of cosecant x? Negative cosecant x, cotangent x? That looks problematic, doesn't it? I pulled this problem right out of the book, so. Why do you think I split that up like that and rewrote it all like that?
Cancellation.
I'm just trying to see what's happening. That's all. I mean, when I have cosecant and cotangent, I can't really tell what's going on here. So I rewrote them like this. Look at this. If I take just the 1 over sine and bring it up here, I can leave this one down here. Just bring this one up. What would happen here? Right? If I just get rid of that, I'll leave the negative down there. What is this limit right here? It is 0 over 0, but wasn't that the one that you were supposed to remember?
Yeah.
At the very beginning? If you have like sine x over x, that's going to go to 1, isn't it? 1? And then what about this cosine over sine? If I flip it and bring it up. I get 0 on the top and 1 on the bottom, don't I? So what's happening here at the end of the day is that I've got a 1 here. I've got a negative 1 here. Don't forget that negative 1's here. I've got 1, negative 1, 0 over 1. So what's the answer? 0. I didn't get rid of it. I flipped it up. I flipped it up to the top, multiplied by the reciprocal, and brought it up like this. So look, please make sure you're doing your homework. I mean, a lot of these things you're going to have to see as I work through the homework, you know.
About the homework,
Uh-huh.
one of the videos for L'Hopital's rule,
Uh-huh.
I think it was like the third one, it's private, and we can't like look at
The homework video?
Yeah.
Really?
Yeah, it's like private, and it's just like half the homework. So.
Okay. I will go take a look at that right now. Maybe it is private. Maybe I don't want y'all to see it. I don't know. I will take a look though.